Welcome back to a course on measure theory and integration. In the previous lectures, we have discussed few propositions, and in this lecture, based on these propositions, we are about to solve few problems. Right? The first problem tells us if A is countable, then we'll have to prove the outer measure of the set is zero. Okay. In order to prove this, what are we going to consider? Okay. Let us solve this one. So given A is a countable set, right? Then A can be written as a countable union of singletons An. That is what we mean here is A shall be written as union entrance from 1 to infinity An. So I am just making the union of these singletons and I make this A to be a countable set. We have just made use of the fact that countable union of countable set is countable. Okay, here singleton is basically a countably finite set, right? So this union is of course a countable one. So we write this way, right? So what was the proposition that we see previously? This quantity is happening to be true, right? So by the above proposition, that is like, if you want you can just quote the, actually you will have to quote this statement an is a countable collection of real numbers, then we can write outer measure of a, which is nothing but outer measure of union n runs from 1 to infinity an. This is smaller than or equals outer measure summation n runs from 1 to infinity measure of individual sets, that is singletons an, right? Outer measure of the singleton is what? That is 0, right? So summation n runs from 1 to infinity L of length of singletons. Length of singleton is 0, therefore summation n runs from 1 to infinity 0. So which happens to be 0, right? So what we have here is measure of A smaller than or equal 0, but by the definition of outer measure is always a non-negative quantity. Hence, outer measure of A is 0. Right? So this is what we intended to prove. The next problem tells us the set closed interval 0, 1 is not countable. How are we going to do it? Okay, so we'll have to do this by summing. Okay, so do you get any idea? Okay, suppose the contrary, that is 0, 1 is countable. If it is countable, then what happens? Outer measure of 0, 1 is 0. But the outer measure of any interval is its length. Therefore, outer measure of 0, 1 is length of 0 1, that is 1 minus 0, which happens to be 1, and that is not equal to 0. So this is, let me mark that as equation 1 and this as equation 2. Both 1 and 2 can't be true simultaneously. Hence 0 1, this interval is not countable. So this completes this problem. Okay, next we have the set of irrational numbers in this interval. Now we'll have to prove m star of a is 1. Okay, so here this is quite simple. Let us disjointify. Okay, now we are about to write this a. Okay, a is given to be 0 1, right? Sorry, irrational numbers in 0 1. So this may be written as this interval intersection q, okay, union this interval intersection q complement. So this one I take it as b, and this one is given to be a, only the irrational numbers, right? So this 0 1 is now union of these two sets where this b and a are disjoint. Thus outer measure of this closed interval 0 1 is outer measure of b union a, which is nothing but the outer measure of b plus outer measure of a, right? We know this is length of 0 1. Okay, what is this? Okay, let me write, this is simply m star of b and this is m star of a. So this is what we'll have to calculate. So let me keep these things as it is. Here we'll have to observe one thing. Observe 0 1 intersection q is a subset of q and is infinite. This is an infinite set, right? Every infinite subset of a countable set is countable. Therefore, this set is countable. Therefore, m star of this is our b, right? So m star of b is 0. So plugging in this information into it, what we get? We get 1 equals 0 plus m star of a. Therefore, m star of a is 1. So this tells us what? The set of irrational numbers, the set of irrational numbers in 0 1 has the outer measure 0. Okay, next we have a problem. Actually, I think I'm going to leave this as an exercise to you people. But okay, here we are given any set A and epsilon is some positive quantity. Okay, then we have an open set O such that A is contained in O and this inequality holds. Okay, you will have to pay clear attention to this. Here we have a set G. This G is a member of G delta. Okay, now you must be very clear with the ideology of what that set G delta is. Okay, What I'm saying is that this G is a member of G delta. Okay, so the definition, let me give you: a set of real numbers is said to be a G delta set provided it is the intersection of a countable collection of open sets. Okay, so I leave this as an exercise to you people. You just try it, and if you are not able to get it in a proper way, just ping me in mail or whatever way possible. Let us discuss it in the next lecture. Thank you.